I'm Zach Anderson, and for my Lab 9 project, I made a remotely operable turret. The turret consists of a gutted gel blaster that's mounted directly on top of a stepper motor. I'm also using an external webcam, which, when connected to my laptop, allows me to overlay a reticle to a processing window. So when I turn the potentiometer, I'm obviously rotating the turret, but this also allows me to sweep a reticle across the screen, which corresponds to where the gun is aiming. So basically, the reticle and the gun are both mapped to the potentiometer. I also have a button for an input, which is connected to this integrated circuit, and all it does is complete the circuit and allow the gun to fire. Here's a better look of how the potentiometer interfaces with the turret, as well as the reticle or crosshair that you see on the processing window. Here's a demonstration showing all functionalities operating together. So you turn the potentiometer, which rotates the turret, and using the processing window, you can aim and select your target. And once you've done that, all there's left to do is press the button to fire. While the gel blaster mounted to the turret is fairly inaccurate, you'll see that one of the shots landed just above the bullseye, so our method of aiming is not too bad. Moving on to the wiring on the breadboard, we've got the L293D H-bridge hooked up to the stepper motor, and that's wired in the exact same way as Lab 7, except for pin 8, we got it hooked up to a 12-volt DC charger, just because it's a larger stepper motor, requires more voltage. So we've also got this potentiometer, which you saw before, and that would be standard. It's just hooked up to analog pin 0, except for the fact that I included a low-pass filter here with a 1 microfarad capacitor and 10 kilo ohm resistor. And the idea there is just to smooth out the input for the potentiometer so that the gun's not twitching when it's still. And yeah, finally we got this button here. And like I said before, it's literally just connecting this, it's connected to this integrated circuit, and you literally just close the circuit, and that's how that works. Starting off with the Arduino code, we've got some tuning constants, such as step delay, which controls how fast the motor steps, max steps, which defines the total range of motion in steps, and that's currently 100, which I found corresponds to roughly 180 degrees. And then we've got number of samples, which represents the number of readings per average value for the smoothing in the loop function. As I alluded to previously, I use a smoothing technique called a moving average, which stores the last 10 readings in an array and keeps a running total. Every time I get a new value, I subtract the oldest one in the array to make room for it. And then dividing the total by 10, I get an average value of those readings, which reacts more gradually and dampens the impact of extreme values caused by noise. So that the stepper motor actively seeks to match the rotation of the potentiometer, I define a variable called current step, which starts at 0. I then use two if statements to update the current step value based on whether it's larger or smaller than the target value. This allows the code to know where the stepper is and rotates it until the stepper's position and the position of the potentiometer match each other. The actual rotation of the stepper is controlled by the two functions step clockwise and step counterclockwise. The only difference is one of them decrements and one of them increments the step index, which just changes the order in which run step activates and fires the coils. Finally, in the processing code, I use processing video library to select the appropriate camera for the webcam input, and processing serial to receive the constantly updating current step value from the Arduino code. I then take the current step value, which represents the current rotational position of the stepper, or where the gun is aiming, and map it from a range of -15 to 30, which represents about 180 degrees of turret vision, to the screen coordinates. I flip it horizontally so that the direction matches where I'm turning the potentiometer, and constrain the X position so the crosshair fits within the window and doesn't go beyond that. Finally, I draw the webcam image on the window and call the draw crosshair function to draw a red triangle using the current crosshair X value. This triangle always stays vertically centered and moves horizontally as you rotate the potentiometer. This concludes my project presentation. Thanks for watching.